Thank you, Laura. I'd like to thank the organizers for inviting me to take part to this nice program. Although my research projects are a little bit not in maybe not in the mainstream of the activity, but I would like to convince you that correlation functions in supersymmetric gauge theories are very close to program. So since there are not so many specialists in this topic here, and there will not be so many talks, I will try to give a kind of overview of what is done in this field and what is the language that we are using, which can be a little bit different from the language that is spoken here. So I will present some work that's a little bit old already, 7 years ago. Ivan Kostov and Valentina Petkova, and the more recent work on correlation functions in a theory which is not n equals 4 super Yang-Mills theory that you know well here. And also I will mention some work in progress on the subject of correlation functions. One of them will hopefully appear in the end of March, and some other project that is slowly advancing. So why we are studying these theories, supersymmetric gauge theories, we are trying to learn about physics and mathematics of particle, the theories that are underlying particle physics, like QCD. So we are trying to study theories that capture the physics of these theories, but they are exactly solvable in some sense. They are simpler from the mathematics and the physics point of view. And also they are dual with string theory, so we can learn a lot of things. There is an exact duality between n equals 4 super Yang-Mills theory and string theory. So we are trying to get insights from both from the perturbative treatment of these gauge theories and from the strong coupling version theory dual of them. So of course the n equals 4 supersymmetric Yang-Mills theory will appear as the main example of on which we test ideas, but other deformations and versions of it are interesting, and we can learn from them. So yeah, that's the type of theory that we are experimenting on. For these theories, integrability, the method that I'm going to explain allow to find the the equations that are obeyed by the spectrum of conformal dimensions, because this theory is a conformal field theory in 4 dimensions. So there is a collection of conformal dimensions. So that I will mention the way that the information about the spectrum is encoded in the quantum spectral curve, and how this is obtained from fusion properties of the transfer matrices associated to the thermodynamic Bethe Ansatz theory. And once similar kind of methods are developed for correlation functions, but the final answer is not yet here, the approach that works well, which works best is for the correlation function is the hexagon expansion of correlation function. So there is a similar expansion for amplitude that's known under the name of OPE, or pentagon expansion, and there is a close connection between these two approaches. So the plan is to, well, I will review the formulation of the spectral problem as of n equals 4 super-Young theory in terms of an integrable spin chain or integrable 2D field theory. So this serves also to introduce the language that I'm going to use. Then I will explain how this geometric decomposition of correlation functions in terms of hexagon works. And then I will give some example where this method works and where we can get a nice closed form answer for some relatively simple correlation function. Then I will explain our work from last year on orbifold of n equals 4 super-Young mills and how to get results from supersymmetric localization were obtained recently on for this theory. And I will explain how to retrieve, how to reformulate these results of supersymmetric localization in terms of this hexagonalization program. And the last part of the final part of the presentation will be will discuss this more recent projects on the origin limit of the disk correlators and the strong coupling limit via the so-called chi system. I will try now to explain how to formulate the spectral problem of n equals 4 super-Young mills in terms of a spin chain. So the theory has has a collection of fundamental fields. So you probably know the gauge field, whose quantas are the gluons, for which the scattering amplitudes are computed. The gluon in this theory come with a whole family. Partners as super partners, so they are there is a set of bosonic fields with indices that go from 1 to 6 and some fermions that I will use a little bit less here. These fields are matrices, NC by NC, NC is the number of colors. So we are going to look at the limit where the number of colors, the rank of the gauge group is large, infinite. And we are looking at a limit when this combination of coupling constant and rank of the gauge group stays finite while we send infinity. So this is the planar limit of n equals 4 super-Young mills. And this is the limit where the integrability was found to function, at least to function the best. So the way to map this theory to an integrable spin chain of the type, I mean, it's very similar to what people study in condensed matter for one-dimensional magnetic systems. So this isotropic Heisenberg spin chains, which is more than 100 years old, is a prototype of this integrable one-dimensional integrable models. So in our case, the states of the spin states are the role of the spin states are played by the type of field that we have here. So we, essentially in the planar limit, we are interested in single trace operators, which are traces of products of these elementary fields, situated at the same point in space-time, and they can have different orientation in the space in this internal space that can be also interpreted as a target space of corresponding string theory that's dual to n equals 4. Okay, so we are taking this combination where the orientation of these fields, these fields is encoded in some vectors y. Take the traces, and this is our spin chain state. So at weak coupling, when the coupling constant is small, we can, or when it goes to 0, we can compute the correlation functions of these single trace operators by Wick theorem, by taking contractions of spins from one operator, one chain to another, and the dimensions, conformal dimensions, or in this case, are just the bare dimensions which are related to the length of the operator are involved. So we can keep in mind that we have this contraction here, and we have a length associated to this to the operators that we are considering. So it's useful to imagine this two-point correlation as some world sheet of a string propagating in space-time. So via the ADS-CFT correspondence, the correspondence with strings, this analogy can be made more precise, because for particular states of for particular operators that we consider here, the associated, the dual object in string theory is a string propagating on the world sheet. So in the, if we go at arbitrary coupling, the point correlators will still be of the same form. We'll have some space-time dependence with conformal dimensions appearing in the exponent here, and this exponent here is the energy of the spin chain. So we can imagine this propagator here that it's mapped to a overlap of two states of the spin chain. So a special role of in this game is played by the half BPS states, where we take this again this single trace operators with some particular polarization of our fields, and now you see that I'm taking for all the in state the same orientation, vector y. So these play special role because they play the role of what is called ferromagnetic vacuum of the Heisenberg spin chain, and the excitations of the states of this system can be described in terms of spin waves or magnons. These magnons will appear often in my presentation. So these excitations are called magnons, and because I have many kinds of indices here of the operator, they will also carry flavor indices, and these flavor indices belong to PSU22 square. So I call one of them left and one of them right. So these operators come with different flavors, and scattering of the flavors of particles, spin waves with different flavors is described by the scattering matrix that was determined by Bizard, and this scattering matrix obeys the Yang-Baxter equation, and that's how integrability appears in the story. So once we have this formulation of our system as an integrable spin chain or integrable two-dimensional field theory, there is also a counterpart on the string theory side. So the problem of finding the energies here can be reformulated in terms of fusion relation for transfer matrices. So the machinery of algebraic Bethe Ansatz uses these transfer matrices with indices which are so the indices are a priori two integers. But in fact, in this particular case, they are restricted to this gray area here. So the relations that are obeyed by the transfer matrices are of this Hirota type. So there is a variable here U which encodes the momentum of the magnons. This variable is called rapidity. So the transfer matrices obey this type of relation. So if you neglect the shift here, these are just relations obeyed by the characters of SUN representations. And also these fusion relations can be written in terms of Y systems. If you make some transformation on Y's. So these relations, if you don't specify what are the analyticity constraints, the solution is not unique. But if you bring in the analyticity constraints which are associated to the particular system that you are studying, these relations are very general and are obeyed by all the transfer matrices for systems with SUN symmetry. So once you have to bring the analyticity constraints which tell you what is your system that you are looking at. So that's one important aspect. Also, it's miraculously the only way that the coupling constant appear in this equation is through this variable that is combined. You take the rapidity variable and you make this Joukowski transformation, and in fact the equations depend on the coupling constant only through this variable Joukowski variable. So if you are trying to solve these relations, A and S are take infinite number of values, so it's not easy to put it on a computer and solve. People were doing this in the beginning, but it's still complicated. So in the end, the T matrices can be written in terms of some simpler objects that are called Q functions, which are related to T via the Baxter equation. And in the end, these equations here can be encoded in what are called QQ relations, which are Wronskian relation on the different types of functions. So when you're doing this, you're reducing the huge amount of indices here just to basically you have 8 functions that you have to use to generate the others through the Wronskian relations, and then impose some analyticity constraints on them. So this is what determines the spectrum and what was achieved about 10 years ago. So this technology was developed in the 90s for the integrable 2D field theories. So there is a whole story behind it, which I didn't mention here, but that all that's behind this relations is contains decades of work and understanding of the description of integrable field theories. So that was for the spectrum. Now for the correlation functions, where we need something which is a little bit more complicated. So now the 3-point function. So the information that we need now. So is we are dealing with a conformal field theory. The dependence on the space-time coordinates is encoded in this dependence here. We now can consider these deltas here that they are determined through the spectral problem. So what we would like to compute are these structure constants here, which in general depend on the coupling constant. So the way to the most efficient way to compute this object in general, the prescription was given 10 years ago by Basu, Komatsu, and Vieira, and it can be illustrated on this well, in the case of the 3-point function. So now I'm taking 3 different spin chains, and I want to compute the overlaps. So in condensed matter, this is not what people would like to do. So it's a little bit less studied. I mean, you are not doing something as violent as changing your system by fusing two systems together. So yeah, so that's something that for string theorists is more natural, because this what I draw here looks like a string vertex, string interaction. So the idea is to just transform this object into something simpler. You cut the pants open into 2 pieces, hexagonal pieces, and then you imagine that you want to glue together. Once you know what each of these hexagons contributes to, you would like to combine them to get back the 3-point function by gluing the hexagon with some transition factors, which will take into account how many contractions. Here you have these weak contractions that I was showing on the first slide. So yeah, so that's how you would recombine 2 hexagons with the decorations, Magnum decorations to reconstruct your 3-point function. So when you are cutting open here the surface, you start to reveal the excitations that circulate inside this worldsheet here. So these particles that are here are, I will call them mirror magnons, because they appear in the mirror. What is called the mirror regime of my field theory that I have here. And you see that when you are cutting here, you have to distribute the magnons in all the external magnons in all the possible ways between the two hexagons. So you can see this if you want to look back to your 2D integrable field theory representation. This object here, you can interpret it as a non-local form factor. So this kind of object also was computed in was considered in condensed matter application in order to construct to compute entanglement entropy. So you can imagine that this is a piece of the worldsheet where you introduce some curvature defect in the middle. So this is and you have three different incoming states. So if you are comparing this with local form factors that people use in condensed matter, these local form factors will be more associated to some a rectangular piece of the worldsheet that is here. So when you have one of these form factors, you also so if you know what this object is when you insert your excitations on a side, in fact there is a prescription how to send them from one side to the other, and this is what sends a physical particle into a mirror one. And this helps, in fact, to get a solution for these objects for the form factor from form factor axioms. So the result that Basu, Komatsu, and Vieira obtained is for the hexagons. So the hexagons have indices, this PSU22 left and PSU22 right indices that I mentioned earlier. So the hexagon has a part which is a scalar, which contains is a function of rapidities, and then there is a part which contains the indices and which is given by the Bizart matrix, S matrix. So this is to say that this object is known explicitly, although the functions here are complicated, but it's something that we can use for particular, if we have particular function to compute, we can take an approximation of the general formula and compute with it. So, okay, what this is good for? You would like, of course, to compute higher point functions. So a way to express higher 4-point functions by this hexagon decomposition was proposed in 2016 by two groups. So if you take the 4-point function, the way to split this function in hexagon was proposed in this picture from the original paper. So this you can see this the composition as a triangulation of the sphere. So you have 4 points of the sphere, which are the insertion points of these operators, and then the cuts here. The cuts are associated with some edges that connect different points. And well, once you do this, you plug in your expression for the hexagons, and you start to do perturbative expansion, and you see that you can by summing over these mirror magnons that circulate here, you start to generate objects that you already know from field theory, Bloch-Wigner functions and other integrals that you usually associate with Feynman integrals. So this is a promising feature of this decomposition, but if you want to do this expansion systematically, there are a lot of complications that come with them. So one of the complication is that when you are starting to glue hexagons around the insertion point, you potentially get divergences which are associated with the structure of the operator inserted. So this is related to the TBA structure, to the TBA for a particular operator that you are inserting. So you should be able to get the story of the fusion matrices that I mentioned previously from the gluing of the hexagon. But this was not done explicitly because it's a little bit involved. So this is one of the difficulties. So when if you want to get rid of this, not to care about it, you can start with looking at correlation functions of BPS operators. This vacua that I was mentioning in the beginning, because they don't have these divergences. And yeah, so you get rid of the excitation structure of the insertions, and then you will get some object that depends on two sets of cross ratios. One for the x variables, the usual cross ratios that you see in amplitudes, and also you have cross ratios for this variable y, which will also appear in the correlation. So, any question on this part? Yeah. Okay, so since the general structure is still hard to disentangle, then you can look at some limits. So one thing is you can do is to separate the sphere into simpler objects, which are just you get disk geometry. If you manage to to separate the contributions that come from two different pieces of the sphere, then you get something which is simpler because you don't have this complications of magnons wrapping around the insertion points. So one way to do this is to set the length of the operator equal to 2 and send a collection of distances to light-like distance, and then the results should reproduce amplitudes or Wilson loops, which are dual to amplitudes. The other way to do things is to send the length of these bridges here to some of the bridges to infinity to decouple two hemispheres. So this was what Coronado proposed to do in 2018, and this was later related to some duality with 10-dimensional scattering amplitudes on the Coulomb branch. So that's a long story, but the way to get you can get a simpler version of the sphere correlation functions by sending them to a disk to the disk geometry. So for 4 points, this this object is relatively simple, so it was possible to find the result in closed form and for any value of the coupling constant. And well, for n bigger than 4, that's still work in progress. So if we are looking at the, let's look at the case of 4 points. So we are now left with this quadrilateral which is this. So the 4 points are now their coordinates can be. We can use conformal invariance to send them to 0, 1, infinity, and z. So the cross ratios are depend only on two variables z and z bar, which can be parameterized in this form. So if we are in Euclidean regime, this phi will be real. If not, it's imaginary. So we have the cross ratios for the space-time and also the cross ratios for the y's, for the r charges. So in this case, well, you want to do the procedure of summing over all the mirror magnons on this diagonal here. So this diagonal can have a bridge length, arbitrary bridge length that I denote with L. So you do the computation here. That's what we did with Ivan and Valentina years ago. So you get this object can be written in terms of a Fredholm determinant. So it's a Fredholm determinant of a kernel. So the expression was put in this particularly simple form by Belitsky and Korczynski. So this matrix here that you are computing the determinant, semi-infinite matrix, is written in terms of Bessel functions. The two Bessel functions here have the same parity. That's an observation. And then these objects are very general, and the information about the object that I'm studying is encoded in this function here, chi of t. In fact, you can also put the dependence on the coupling constant inside. So chi of t contains all the information of the problem you're studying. So for this object, this particular object, the function chi of t is written in this form. And if you change this function to some other value, you get other objects that appear in n equals 4 super-Young Mills, like circular Wilson loop, all kinds of objects. One thing that one observation that was made by Coronado when in the original paper of about this correlation function was that if you are looking if you are taking the null limit where the distances here on the frame, all the distances go to like. So this will be this will correspond to sending taking this phi to be imaginary and sending it to infinity. So if you are looking at this limit perturbatively, first you see that the behavior of the octagon when the bridge length is equal to 0 goes like y square times some function on the coupling constant that can call gamma oct, and then there is also it's also there is also a dependence psi square, so psi is the log of z bar. So there is this beautiful expansion in the squares of logs of the cross ratios. And in this paper by Lipsky and Korczynski, they were able to, using nice methods of analyzing Fredholm determinants, they were able to obtain the explicit all-loop formula of this gamma oct and also of the constant here. Yeah, that's an object which, in fact, belongs to a larger family of kernels that come from integrabilities. Of the first occurrence of this kind of object was the Caspar-anomalous dimension that appeared in the early years of integrability, and which helped to set up the details of the integrable model that's behind the ADS-CFT. So people knew this BS Caspar-anomalous dimension. Then we get this gamma octagon, but there is a whole family of tilted cusps that were discovered in a work by on amplitudes by Basso, Dixon, and Papatanassi. Another remark that I wanted to make is that if you are looking at this octagon and you're expanding it in powers of G, you'll get expressions in terms of ladder integrals and the determinants of ladder integrals that are called the Basso-Dixon integrals. So this object is can be written in terms of objects that come from Feynman integrals, and also it has other nice properties. For example, it satisfies some recurrence equation that looks a bit like the equation, but not exactly. So this relation here was used by Korczynski to find the lattice path expansion of the object of OL when you are increasing L from 0 to arbitrary value. And also it has resurgent properties that are still being analyzed. Okay, so that's a nice object that we can compute starting from gluing hexagons. So I will try to mention another. So I was saying that in other theories that are integrable, this object appears. So that's the case of orbifold of n equals 4 super-Young Mills, in which, so if you are looking at it from the point of view of a gauge theory, so the gauge group is k copies of SUNC, and there is some action of the. So it looks like a twist of the original theory, where the twist will be some diagonal some diagonal matrix with which has the values given by the kth root of unity on the diagonal, and the fundamental fields have some prescribed behavior under this twist. So the supersymmetry in this case is reduced from PSU22/4 to SU2,2/2 and times SU2, and the Magnon symmetry is twisted, so it was PSU22 times PSU22. So now there is a twist which acts on the right part of this symmetry, which is given by some diagonal matrix that contains the eighth root of unity here. So this theory is expected to be integrable when the gauge, the couplings of these gauge groups are equal. There was a renewed interest in this for this theory because you can make some computations from using localization, the matrix model, Stone matrix model obtained from supersymmetric localization. And if you are doing this, if you are using this model, you can compute several things, including 2.2 and 3-point function for some special operators, which will be equivalent of the vacuum, so BPS vacuum operators. So now you have the twist, so you can build your operators like the vacua that I was mentioning previously. Take operator to a power L and they take the trace. Or you can insert power of this diagonal matrix and twist the operator. So this is the twisted sector of this theory. The conformal dimensions are still the one that they are still protected by supersymmetry, so they are constant. But the 2-point functions are not protected. So except for the untwisted sector, where you get exactly the same thing as for the n equals 4 super Yang-Mills, an expression that doesn't depend on G. While if you are computing this overlaps, these 2-point functions for the twisted sector, you get, I represent it with a cylinder with a twist inserted. So the 2-point functions take the form of these ratios of spectral determinants, where the kernel here is the same that I was mentioning previously. L is essentially the number of fields here, and you have to put the cross ratios to some particular values. And the expression depends on these numbers S alpha, depends on the twist through S alphas. So you see that when alpha is equal to 0, the untwisted sector, these two determinants trivialize. That's the expression that was obtained by supersymmetric localization and was checked by perturbative computations. So for the 3-point function, well, 2-point function is relatively can be considered as a normalization, but if you are looking now at the 3-point function of the same type of operators, by conformal invariance, you get the same space-time dependence, and then you get some the structure constants which depend on now on the length of the operators that you insert here, and the twists that you insert. So there is for some reasons you have to consider extremal cases of correlators, because you cannot contract the fields otherwise. So there is R charge imposes R charge conservation imposes this relation, and then the conserved zk charge imposes that the sum of the 3 twists is 0 modulo k. The feature that was that comes from this computation is that the 3-point function factorizes in 3 factors that correspond to each of the operator, and each of these factors takes again this expression in terms of Fredholm determinants, and now, well, you see that there is a part which depends on the square root of the spectral determinants in this way. So these look very much like octagon expression. So okay, the question is, can you obtain them from integrability? And well, so that's what we did with Gwenaël, Ferrando, Shota Komatsu, and Gabriel de Fundes. We took the hexagon machinery and we started to compute by inserting this twist. So you cut the 3-point function into 2 hexagons. You insert the 2 twists on 2 bridges, and then you sum over all the mirror magnons in the intermediate channels. So you try to reproduce this structure here. So we see that different factors in the result have different origins. So there are some contributions which are clearly from summing magnons on each of the bridges, and this is the computation we did with Ivan and Valentina. This reproduces this part here. But there are other the square roots here. They are coming from some contact terms that you see from the magnons coming from different bridges around the particular operator. So there are 3 different types, and these are associated with these contact terms that potentially give divergences. Here they don't give divergences, but they give some finite contribution, but that you also have to compute from contact terms. So this contribution will give the square root here. And there is another term that's curiously, so if you are looking at your geometry, you see that you have only 2 bridges that are active, that are contributing to the 3-point function. But in the final result, the final result is symmetric. So you also have a bridge-like contribution in this factor here, which is associated to this operator. But you don't have a bridge that looks like this in the final. So there is another more complicated contact term that. So okay, so we understood how to reproduce all these terms. So that the use of this computation was to see that there is a particular configuration where you can do this computation systematically, and we got some All-Rup conjecture for this wrapping contribution in terms of mirror as magnon matrices. Well, it's rather technical point, but it was important for the understanding of how these objects contribute. So in order to achieve this, to be able to take this contribution systematically into account, we had to do some regularization, and this is essentially to take glue 3-point functions together, 2 copies, compute the square of the structure constant. You build some torus, the genus 2 torus. You have these twists that run around some of the cycles of the torus. You cut around, insert mirror magnons, use the hexagon formalism, and then you get some result. So okay, probably this is not so interesting in the larger. But it can be done. So that's a an important point that that we can go this direction. So now I would like to mention what can you do for polygons. So I explain you what to do for the quadrilateral. You can find an exact solution. What can one do for higher polygons? Again, in the disk geometry. So for the next sizes, decagon and dodecagon, there are perturbative results. To do the expansion systematically is complicated. So if you are doing hexagon tilings, it's easier to consider 2D kinematics. And yeah, so if you are doing hexagon tiling, you're cutting your surface into hexagons. So now my hexagons will be just triangles. I will forget about the structure. Of the corners. So this is what was a hexagon before. So now this cutting of the surfaces amounts to a triangulation. So now we are in 2D. This I can use for the position of the corners. I can use x's, which are complex coordinates. So from this, for each of the edges, I can introduce a cross ratio, which is dictated by the quadrilateral that surrounds let's consider this cross ratio here. So I take the quadrilateral that surrounds it, and I define the cross ratio associated to this edge by this ratio. So you see that if I flip the edge, if I consider a triangulation cutting this way, the corresponding cross ratio is the inverse of the original one. And if you're looking around the coordinates, the cross ratios behave as Fogg-Goncharov coordinates under the mutations that are associated to the flip, to the change of triangulation. So this indicates that cluster algebra structure is the right language to formulate these objects, but still then we have to build around this cluster algebra structure in order to find something that is interesting for our correlation functions. So there is from the experience with scattering amplitudes, there is a limit where one can send as many of these cross ratios. In fact, the combinations of ZZ bars, if one sends as many of them to zero as possible, then the resulting object has a nice particular structure. So that would be a higher point version of the null octagon limit when the result depends only on the square of the logs of the cross ratios. So in this case, so in the amplitude case, similar formula appeared where so you have a formulation where the log of the correlation function, well, the amplitude in their case, is written as a quadratic object in the logs of the cross ratios. And then this object is multiplied by one of the tilted cusps. Yeah, so there are combinations of tilted cusps that appear in the limit, and that behavior is encoded in this function. So in order to treat all the cases in the same time, you can write the result in terms of a rational function of z's and log of u's. This function has poles at the roots of unity. Z is equal root of unity essentially, and then when you take the residues of the poles, you just get a function of quadratic function in logs and the corresponding tilted cusp. So this is the structure that was obtained in the amplitudes, and we are seeing a similar behavior for the disk correlation functions. So the data supports the fact that similar structure should hold. So that's one of the projects that is in progress. So there is a presentation by Benjamin Basso at IGST where more details of this work is given. So different, very different limits that we are we analyzed, and the paper will hopefully appear next month, is to look at the strong coupling limit. So if you are looking at the strong coupling limit, if you are thinking then analogy with the amplitudes, at strong coupling, the amplitudes are this. You can take the limit of a semi-classical string limit, and these are some results that were obtained in more than 15 years ago by Aldai, Gaiuto, Maldacena, and then Vieira. So the amplitudes at strong coupling are written in terms of a Y system. Not exactly the one that I was mentioning in the beginning, but a different Y system with a kind of mysterious origin, if you want. So there are derivations from the pentagon expansion for the amplitudes at coupling in this paper and the related paper. The case of the amplitude is a bit complicated because there are a lot. So there is a lot of structure. So essentially, what we are obtaining, what we are looking at, is a simplified version for the simplified case where the kinematics is two-dimensional, so the formulas are a little bit simpler. So also for the octagon at strong coupling, there is a simple answer that was obtained in 2019 by this generalization of this formula for the amplitudes. So this is for the disk geometry, but also for the sphere geometry. I was saying we get a TBA-like system. Now the inspiration of we came to understand that the systems that we are finding, they are very similar in their mathematical structure is very similar to the Chi systems that were considered by Gaiuto, Moore, Naitzke in the series of papers in 2008, 2009, where they are looking at the counting of BPS states in N=2 theories, and they are developing a technology called dual crossing. So we are finding a very similar structure as that was obtained by Gaeto Murnitsky. So in the case, we shortly after this series of papers appeared, this technology was applied by Caetano and Toledo in a beautiful paper where they obtained a chi system for correlation functions for 4-point function in ADS2 kinematics, so simplified kinematics, from semi-classical string analysis, a little bit like for the amplitudes. So they consider this kind of triangulation for the sphere. You have the 4 insertion of the operators, and then you decompose it and triangulate the sphere in this particular way. So the system of equation that we get is looks like this, where chi are now functions that depend. So they depend on the rapidity. Before it was called u, now I call it theta because it's a particular limit strong coupling. So this is a set of difference equations on this variable theta, which contain some combination of functions of the i's on the other edges of the triangulation. And this is essentially, if we are working in the ADS3 times S3 kinematics. So if we are taking, if you are going to the limit that was studied by Caetano and Toledo, we are getting similar equations. So that's our result. And so these chi functions, I don't know if how much they are known in this community, that they are also Fock-Goncharov coordinates, but they depend on this variable theta. So they have a very nice transformation properties with respect to changes of triangulation, which is not the case for the Y systems. That if you are working only with Y systems, their behavior under change of coordinates is not so good. Okay, so sorry, I'm a bit over time. I'll try to wrap up. So I hope I convinced you that well, integrability for correlation functions is interesting, and there is some connection to amplitudes and the mathematical formalism that is behind the amplitudes via this origin and this strong coupling limit. So yeah, there are other theories that can be described with the same formalism. So the same hexagon approach was set up for the n equals 2 the orbifold for non-BPS operators. So it's in the end, what we would like to have is a connection between the information that comes from the quantum spectral curve, the Q functions for the operators insertions, and the correlation function. So there is an alternative approach based on separation of variables that is pushed by groups, and hopefully that provides a different perspective that would be useful for other for particular. Thank you for your attention.